Alright, in this exercise what we're going to do is we're going to implement PI control on our temperature control lab unit. Compared to proportionally control, PI control tries to eliminate the persistent offset that can occur. Let's say that my set point is 50 degrees on my temperature control lab unit, and as I approach 50 degrees the heater is going to slowly turn off as that proportion between the set point 50 degrees and the actual temperature gets smaller and smaller until there's a point where it reaches a steady state and isn't quite able to reach 50 degrees. The integral portion, as we've talked about hopefully earlier in the course, allows us to account for that persistent offset, that consistent underperformance, if you will, and push the heater up until it reaches the set point. So we'll talk about tuning. So objective of this exercise is to go from, I'll make it a little bit bigger, 23, set our set point at 23 degrees and a step change to 60 degrees. We have three main things in our PI controller. We have our Q bias, we have our proportional term, which is the proportional gain, Kc, times the error, as well as Kc divided by tau I, which is the integral gain from 0 to time. As we've mentioned before, Q bias is there so that when the controller is switched on, it biases it so that there's not a jerk or a sudden change in the original term. Because our temperature control lab is off, we'll have our Q bias as 0. Finally, we'll talk about tuning a little bit afterward and regression. We talked about regression earlier, but we have some basic tuning correlations to help us understand what Kc and tau I should generally be depending on our system. So we'll use those in our system as well. First of all, we'll go ahead and we'll fill in the values for Kc and tau I and Pi in the equation below and implement anti-reset windup. So we'll go ahead and start executing this. First thing we'll do is just set up our system. We'll clear all initial variables and set up a CSV file name so that as we run the temperature control lab, hopefully we'll only have to run it once. So I'll go ahead, I'll change my Active Directory to lesson 12, and we'll go ahead and we'll first run this first section. Alright, we ran into an error, so let's go through this. The first thing it will do, and this should be pretty common now, is we'll try to read a saved matrix. That saved matrix will have the time, the heater setting, the set point, the actual temperature, the error, and the integral of error at any given moment in time. If that can't happen, we'll have this catch, so it'll try to read that matrix. If it can't read it, it will go on to this catch portion. The first time we run it, we'll have to run this catch portion. So the first thing we'll do is we'll write in our Kc and our tau I. Then we'll go on, we'll have a timer for 600 time points, and we'll go through with timing the temperature control lab as well as all the values. Then we'll go on and we'll implement our controller. We'll gather the error as in the difference in temperature, dt. We'll take our temperature, we'll put it into our array E1, which is the error, integral of error, and Q1, which is the heater setting using our PID. And finally, we have anti-reset windup. So let's go ahead and let's look at each of these sections now. If you remember in our parameter fitting exercises, the gain for our temperature control lab is about 0.9. And that's just meaning that for every percentage increase in heater temperature, the temperature should increase by 0.9 degrees Celsius. So it's that input to output ratio. Hopefully that makes sense by now. And if we look at our tuning parameters, Kp is the process, that's the 0.9. So our Kc should be 1 divided by 0.9. So I'll go ahead and put that in this box. 1 divided by 0.9. Our tau I, that's our process time constant, and that's about 175, 180 for the temperature control lab. Again, that's the time it takes us to reach 63% of the way to the steady state condition from when we start a step change to steady state. We've talked about that before. Hopefully that makes sense by now. Again, these are just coming from these rough tuning correlations. Tuning is where we kind of fine tune it. These are just kind of initial correlations to get a rough estimate of what they will be. Afterward, we'll tune it because each system will be different and have different requirements. But this gives us a good start. That's what these tuning parameters are for, or at least these correlations. Just want to kind of put that in context. So we've got our two constants now. We've initialized our arrays in the code. Let's go ahead and look at our control loop now. So for each iteration, we're going to iterate through 600 times, and it's going to first, it's going to take the time with this tick-tock. It's going to look at the difference in temperature and record the temperature. So first we want to gather what our error would be. Excuse me real quick, I said this line right here, line 37, was difference in temperature. That's difference in time. I don't know why I said that. I just realized that hearing myself. This is the difference in time, and that will be important for us as we make our integral. We need to know how much time was at a certain error. So first step is error. That's going to be the difference between the set point and our actual measurement. So let's see, our set point array is SP1. So we'll say SP1, yep, at index I, minus, and then our actual temperature, our measurement, which is T1, I believe. Let's make sure, yep, T1. I apologize, I just did something in Python. These should be the round brackets in MATLAB. Let me go ahead, I'll make the code bigger too. All right, hopefully you can see that well. So our error is the difference set point minus the actual measured, so minus T1. All right, our integral. An easy way for me to do integrals is thinking of this as kind of like when you're starting out calculus, those sums, the right-hand sum or left-hand sum. So when we discretize this, our error will really just be the error of the previous step plus our new error. So we'll go ahead and we'll do that. IE1 so I will say IE minus 1. So the integral of error at time I is equal to the integral of error at the previous time step plus the error E1 at the current time step times dt, the time that we were at from the previous time point. And that's just because as we're timing, sometimes it will be longer, sometimes it will be shorter, and that makes sense to me, this kind of discretization. You can think of columns, if you will. In fact, let me see, I should be able to draw. So let's try this. If this is our temperature, there we go. If this is our temperature, we're thinking of each of these time points. Or actually, let's think of this as a graph of error. This is E. And so this part right here is our dt, change in time, and this is the error at I. So hopefully that makes sense. Go ahead, get rid of that now. Finally, we've got Q1. So that's our heater settings. This is where the actual controlling takes place, or the PI algorithm, if you will. Well, we have our Q bias. There's three terms, and we'll go ahead and we'll look up here. This is it right here. So a little bit bigger, actually. Sorry, I'm getting used to the drawing. There we go. So we've got three terms. Our Q bias, which is 0. So this is 0. We've got KC times error, and then we've got this right here. So let's go ahead, and that's KC divided by this, and then this is the integral. The nice thing about storing it in an array is it takes care of all this. So we just have KC divided by tau I times the integral of error. So let's go ahead and let's implement that now. First we've got Q bias. That variable is right here, Q1 underscore bias plus KC. Let's make sure we have that spelled right. KC, yep. times E1 I plus, we'll go ahead, Kc divided by tau I, right? Let's go ahead, this is how I'd think through. Just look at the equation each time, Kc divided by tau I. Times the integral of error. And there you have it. That should be our heater setting. Then we need to implement anti-reset wind up. The whole concept here, and let me go like this real quick. We'll do a little quick drawing. The concept with anti-reset wind up is if we have a graph or a measuring temperature, and here's time. I'll go ahead, we'll switch ink colors for fun. Let's do black. So if black is our set point, let's say it starts here, we have a step change, it goes up to here. We have our actual temperature, so we'll get a new color out. Let's make it green. Green's my favorite color. So we have little error, and as we're going up, all of a sudden, it's going to start working its way up. So if the heater setting, we'll make another separate graph now real quick. It's going to be quite the graph. These are just concepts. Hopefully they make sense once, and then from there, everything else makes sense. This is the heater setting up here, Q. One final color, magenta, I guess. So the heater's going to be off, and let's say it jumps to 100% right here, and then it slowly tapers off. Well, we can't go past 100%, so that's why we're going to clip it first of all and say, even if it tells us we should go to 150 at this point, because of how large the proportional difference is, we have to limit it. So we'll say, okay, set it to 150. And then while it's at 100%, we don't add that error to the integral of error. Now, why wouldn't we do that? The whole point of adding the integral of error is to punish persistent offset. Stuff like this right here, where it's reaching a steady state but not quite the set point. So instead, what we want to focus on is the integral of error only is implemented for those situations. If we use the integral of error at times like this section right here, then what's going to happen is that the integral of error will have to have a similar amount of section as the area right here. Remember, it's the integral, so it's going to be persistent. So it's going to keep on having a negative integral of error, which will mean that to offset that, it's going to have a positive error for some time before the integral of error is 0. And then we're going to have some oscillation as it has to overshoot and then undershoot the set point before hopefully it finally settles out. So that's kind of the downside of PI controllers in a nutshell, and hopefully that rambling makes sense, but I think it's something good to go over. Go ahead and get rid of the drawing. So how are we going to do that? Well, first, here we have the clipping already happening. We're saying Q equal to 0 or 100 if it's over 100. We're also going to say that we're going to implement anti-reset wind up by saying we're not going to add anything to the integral of error if we're in these situations. So all we're going to do is say that the integral of error is equal to the integral of error at the last time step. So IE1 at time point I is equal to IE1 at I minus 1. Hopefully that makes sense, and actually it's the same thing for both, so we can just copy and paste it. Now we'll go ahead, let's just run it and see how our stuff does. There's a problem you probably run into. It's because I changed my Active Directory and I didn't have the TCLab module within it. So we'll go ahead, we'll try again now. Oh, here's another thing. So QI, we started here with QI, and then I started talking about, I'm not sure what happened there, to be honest. So let's fix our QI. Our QI should be our heater setting, KC, times our error, so E1I, plus KC divided by tau I times IE1 at I. And we also need our Q bias, so I like putting that over here. Q bias plus KCE1. Make sure that we spelled everything right. Actually, let's let MATLAB tell us if we spelled something wrong. We'll get an error pretty soon here. Q underscore bias. Q1 underscore bias. Can't do anything right. One thing I like about the live editor is you can see what segment of code is running kind of by this little bit right here. So we seem to be running more than we have in the past, and it seems to be executing our loop. And there we have it. So we've already been going 10 seconds. Temperature is at 27 degrees, and we've got our heater. So I'll go ahead and pause it, and we'll pick it up once we've run for 600 seconds. All right, we're almost done with this activity. We've gone through our time. Notice that the time kept on printing out to the right like this. I've changed that really quick. The problem was there wasn't this dash n to tell it to print a new line after each printing. So that's just something, if you see that, you can fix it yourself. With lab.off, we we turn off the heaters and the LED. And the last thing we tried to do is close lab. You see there's this error that the specified window does not exist. If we look at where we call a TCLab and first connect to it, here, lab is equal to TCLab. So that should be close, or sorry, that close right here should be clear lab. If you haven't seen that before, it's just so that we establish a connection with the temperature control lab. We want to make sure that we close it so the next time we open a connection, it doesn't say, hey, there's already a connection. There you go. And then we've got it saved. Let's go ahead and let's look at our plot now. Finish up this activity. All right, here's our graph. We have our temperature over time. It starts a little bit hot because I accidentally had it on a little bit. So temperature control lab starts a little bit hot, and temperature increases as it approaches 60 degrees. You'll notice there's still some persistent offset, so we would obviously want to tune up that tau I portion. And specifically, we want to tune it up by making it smaller so that the integral has more of an effect. Heater setting increases and maintains relatively constant near 40, but you can tell it's slowly increasing as it's trying to drive that persistent offset away. So it will start to approach 60 and eventually it will get there, just not as fast as we want. And we can see first the error, a little tiny blip, but the integral of error over time is obviously much larger in this situation as it continues to increase. We don't have any oscillation. So there you go. Let me know if you have any comments or questions. I'd be happy to